Trigonometric equations, we're going to look at ones that contain one variable and or are quadratic in origin. Okay, for example 1, nice easy one, solve cos x is equal to a half, and you've got to be very careful here. Look at the bounds, minus pi is less than x is less than pi. So remembering our special triangles, we can see that cos of pi on 3 is a half, and from there that's finding the acute angle first, obviously. And from there we have to look at which quadrants we might be interested in. Now we're going from minus pi to pi, which starts and goes around a whole revolution, but from minus pi to pi. So it's still a full revolution here. Cosine is positive in the first and the fourth quadrants. So that'll be 0 plus pi on 3 or 0 minus pi on 3. Remember, we're going from minus pi through 0 through into pi. So the solutions to our first set of equations are minus pi on 3 and pi on 3. It's also really important to always check that the solutions are within the bounds of the original question. The original bounds were between minus pi and pi. Graphically, this is what it looks like. So if we can graph cos x between minus pi and pi, and y is equal to a half, we can see there are two solutions and whereabouts they lie as well. Graphically, it's much easier to do these questions, but we really don't get into graphing trig functions properly until Year 12 mathematics. So if you know how to draw the quick sketch, it'll help you to check your solutions, but otherwise make sure you're doing the four quadrant thing very carefully. Okay, a second question. Cos 2x is equal to a half. So it's a little bit different now to the first question because we're solving for 2x, not for x. I think the easiest way to do these ones is to first of all change the bounds. So originally we had minus pi was less than x is less than pi, but we want to know what happens for 2x. So we're multiplying everything by 2. Minus 2 pi will be less than 2x, which will be less than 2 pi. What this does, it just means that you don't miss any of the potential solutions to this equation. Okay, so we're going from minus 2 pi to 2 pi. Now if you think about it, that will actually be two full revolutions of our quadrants, starting at minus 2 pi, going through 0, and then keeping going and going through to 2 pi again. So the first one we come across will be minus 2 pi plus pi on 3, remembering that cosine's positive in the first quadrant. So we're starting at minus 2 pi, we're going pi on 3 further up, and that will be our first solution. We then go around, and just before we get to the 0, we'll get 0 minus pi on 3 as our next solution, because that's the fourth quadrant. But we've only done one revolution, so we need to keep going again. So we're going through 0, and then we get plus pi on 3, or 0 plus pi on 3 is our next solution. And we've got to keep going because we get all the way to 2 pi, so it'll be 2 pi minus pi on 3 will be our fourth solution. So we've got four solutions to this equation, but remember, this is what it looks graphically. So we've got cos 2x. Now once again, as I said previously, we're not very good at graphing cos 2x just yet, but we will be much better when we get to mathematics. And what I would suggest then is if you can graph cos 2x, you should see how many solutions you get. So we can see here we've got four solutions between minus pi and pi. So we've got 2x is equal to minus 5 pi on 3, or minus 2 pi plus pi on 3, minus pi on 3, pi on 3, 5 pi on 3. But you've got to be very careful. That's what 2x is equal to. We don't want to find what 2x is equal to. We want to solve for x. So dividing everything by 2, we get x is equal to minus 5 pi on 6, minus pi on 6, and 5 pi on 6. You could check that those solutions actually satisfy the equation by substituting them in, but also really make sure that you're checking that those numbers, or those solutions we've got, those four values, lie within the original bounds, so between minus pi and pi. Our final example is a little bit trickier. Oh, I've got some weird stuff over there, but that's okay. We want to solve cos of 2x minus pi on 2 is equal to root 2 on 2 for the bounds of 0 less than x less than 2 pi. Now, once again, because we're solving for 2x minus pi on 2, let's change the bounds. So if 0 is less than x is less than 2 pi, well, if we multiply everything by by 2, we get 0 is less than 2x is less than 4 pi. Now, that's not quite what we want either. We want to match the thing in the middle of the bounds to the thing in the middle of the brackets. So we're going to take away pi on 2 as well. So minus pi on 2 is less than 2x minus pi on 2 is less than 7 pi on 2. And that tells us how many times we're actually going to go around. 7 pi on 2 is quite a lot. So looking at how many revolutions we'll do here, we've got to go round from minus pi on 2 through 0. So that takes us a whole revolution. And then we keep going to 7 pi on 2, which is almost two, well, it is 2 full revolutions of this particular problem. Now, graphically, if we look at this, and this is graphing the original function, now it looks like a sine curve because cos of 2x minus pi on 2, the translation of minus pi on 2 actually makes it into a sine curve. But once again, we won't learn that until we do it in mathematics. And we can see quite easily that we get 4 solutions, which is, what we should be aiming for. And so you can see once again that using graphs makes this a lot easier. Now, thinking about what values give us root 2 on 2. Now, you have to recognise root 2 on 2 as simply 1 on root 2, and that was a little bit of a trick they put in here for us. So we get cos of pi on 4 is 1 on root 2, and cos is positive in the first quadrant and the fourth quadrant. So starting in the fourth quadrant, we get minus pi on 4. Then going around to the first quadrant, we get pi on 4. All the way around again to the fourth quadrant, 7 pi on 4. And then we've got one more in the first quadrant on the second time round, and that's 9 pi on 4. But that, of course, is for 2x minus pi on 2. So now we have to add pi on 2 to each side to get 2x is equal to, pi on 4, 3 pi on 4, 9 pi on 4, and 11 pi on 4. But still, that's solving for 2x. We now need to divide everything by 2 to get x is equal to pi on 8, 3 pi on 8, 9 pi on 8, or 11 pi on 8. And once again, we have to check, are those solutions for x within the stated bounds of 0 less than x is less than or equal to 2 pi? And they are. Another good check there would be to substitute them in and see whether you actually get the correct answer. And that's what you could do if you're doing this in an exam in your checking time. Back to example 4. Now this one's a quadratic. 2 sine squared a minus 5 cos a minus 4 is equal to 0. Now we're a little bit concerned about this because we don't have something just in cosine or just in sine. So we're going to need to substitute for sine squared. And we know that sine squared a is 1 minus cos squared a. So substituting that in and collecting all our like terms, we're solving for that equal to 0. We don't like all the negative signs, so bring it all over the other side or multiply by -1. And we get a nice quadratic this time. 2 cos squared a plus 5 cos a plus 2 is equal to 0. And that's one that factorises quite nicely for us too. So we get 2 cos a plus 1 and cos a plus 2 is equal to 0, giving us the two different cases that either cos a is equal to minus a half or cos a equals minus 2. Now I'm going to jump over to that right-hand side there because there are no solutions to that. We know that -1 is less than cos a is less than 1. The amplitude of the cosine curve goes between -1 and 1. So we don't even have to worry about the solutions on that side. So all we have to solve now is that cos a is equal to minus a half. And remembering that cos pi on 6 is a half and that cosine's positive in the cosine is negative in the second and third quadrants, we can see that the values we want are 5 pi on 6 and 7 pi on 6.